Good morning, all of you. I am Simi Mathew. I work with Dr. Mathew at the Geophysical Flows Lab, Department of Aerospace Engineering, Indian Institute of Technology, Madras. And the topic of the talk is sea surface temperature anomaly over the southeastern Arabian Sea with the changing phase of the Indian Ocean Dipole. I thank the organizing committee for giving me this opportunity to give this talk. And the outline of this talk will be like motivation and background, and then objectives, and then list of anomalous sea surface temperature characteristic that is associated with the Indian Ocean Dipole. And then I will brief upon the various driving factors that determines the sea surface temperature. And then the heat budget analysis we are carried out based on both in situ as well as reanalysis data. And finally, I'll conclude with summary and conclusions. And the motivation and background for this study is that SST over the Arabian Sea was anomalously high during the southwest monsoon season and fall transition months of 2019. And this warmer SST over southeastern Arabian Sea has favored an excess summer monsoon rainfall. And also we could witness 2 severe cyclonic storms during post-monsoon period. So added up all these factors, I was very interested to understand the reasons behind the warm SST of the southeastern Arabian Sea during the southwest monsoon season as well as the fall transition months of 2019. And in the past decade, the figure down shows the DMI index, and 2016 and 2019 were the extreme strong IOD years. And the objectives of this study is to understand the anomalous warm SST during the spring transition months of negative IOD and also during the southwest monsoon season and fall transition months of positive IOD. And also we try to understand the role of lateral advection and vertical entrainment in controlling the sea surface temperature. And also we try to study the higher cooling rate of the southeastern Arabian Sea during the southwest monsoon season of negative IOD. And we also try to understand the contribution of mixed-layer depth variation in controlling the sea surface temperature. And this is the SST anomaly during negative and positive IOD. The first one is for the 2016, the negative IOD, and you can see the SST anomaly was cooler and during June to September, and during the positive IOD, the second figure shows the SST anomaly was warmer during the positive IOD. And during negative IOD, the cooler SST is almost confined to the coastal region, while during positive IOD, it is into a widespread region in the southeastern Arabian Sea. And this is a region we are interested to look into, that is 4 degree north to 12 degree north and 70 to 78 degree east. And these are the two mooring locations within the southeastern Arabian Sea, that is AD09 and AD10 locations. And then this is the averaged sea surface temperature from the southeastern Arabian Sea. You can see a cooler SST happening during cooling of the SST happening during the northeast monsoon season, and that is very intense during 2019, and that cooling is not that intense during the northeast monsoon season prior to the negative IOD, that is 2016. And this has in turn supported a warmer spring transition months during 2016. And the cooling that is following, that is happening in the following southwest monsoon season during 2016 is very intense. And the cooling is not that intense during 2019, and this has resulted in a warmer fall transition months also. If you see, look at 2019, it is following a warmer SST compared to climatology, and this scenario is followed in both the mooring location like AD09 and AD10 also. And the cooling rate during 2016 some southwest monsoon season is almost 0.65 degrees Celsius per month, while it was only 0.46 degrees Celsius per month in 2019. And also in 2019, you can see an intense cooling rate, almost double the value of that happened in 2016. And the larger contribution for the SST is coming from the net heat flux, and here you can see the net heat flux terms in the first graph, and the various components like short wave in the second, and long wave in the third, and the latent heat flux in the fourth picture. And you can see in 2016 the northeast monsoon season was supporting an intense cooling, but SST was not that much cooling is observed in 2016 northeast monsoon season. And in 2019 it is supporting a warming, but the SST was showing an intense cooling during 2019. And in all these pictures, the blue color shows 2016, and red color shows 2019, and the dashed line represent the climatology. And the spring transition month warming is almost aligned with the climatology. And in 2016 the net heat flux supports the intense cooling, and net heat flux is not supporting that much cooling during the southwest monsoon season. And later in the fall transition months, the net heat flux is supporting a warming, but SST is not that much captured this intense warming. And that is due to one term called penetrating component that is lost below the mixed layer depth. And this term depends on the mixed layer depth, and if the mixed layer depth is thin, the penetrating component that is lost below the mixed layer depth will be very high, while it is when it is thicker, the penetrating component lost below the mixed layer depth will be very less. So we have looked into that component like mixed layer depth, and you can see that the anomaly is very high during the positive and negative IOD years. And you can see in the negative IOD years the mixed layer depth is very thin in 2016, but it is thick during 2019. And this picture is from the AD09 location, while the reanalysis data did capture very well the shoaling of mixed layer depth, while the down picture shows the Ekman pumping, and Ekman pumping clearly supports the thinning of mixed layer depth during 2016. So the reanalysis data is not very well captured the shoaling of mixed layer depth during 2016. And the mixed layer heat budget equation we used is this one, and we have the resultant heat flux and also the lateral advection, vertical entrainment, and the residual term. And then this is a mixed layer heat budget analysis based on AD09 data, and we have the first one is for the 2016 and second one is for 2019. And the black color shows the mixed layer temperature tendency, and we have the red color showing the resultant heat flux, and the green color showing the lateral advection. And then we have the dark blue color showing the vertical entrainment, and we have the light blue color showing the contribution by the residual term. And you can see the northeast monsoon season prior to the 2016 is supporting the resultant heat flux is supporting the intense cooling, but the residual term is compensating those cooling. And in 2019 northeast monsoon season, the cooling is the mixed layer temperature cooling is supported by the residual term and the lateral advection, and the spring transition months almost follows the resultant heat flux, while we can see a larger contribution by vertical entrainment during the spring transition month during both 2016 and 19, and this is almost compensated by the residual term. And in the later half of the summer monsoon, there is a larger contribution by lateral advection, and in both 2016 and 19, and this is compensated by the residual term. And one interesting fact to see is that during September, the resultant heat flux is supporting a intense cooling, and this term is due to the larger contribution of the penetrating component. You can see that penetrating component is supporting a intense cooling almost minus 0.163 during the fall transition months of 2016, and this in turn supported the cooling during September. And then we have during October, it follows the net heat flux term, resultant heat flux, and the residual term is compensating the cooling supported by the lateral advection as well as the vertical entrainment. And in 2019, it almost follows the 1D heat flux during the fall transition months. And we have calculated the mixed layer heat budget analysis based on reanalysis data also. Here also we can see the vertical entrainment is underestimated in the reanalysis data, and also the penetrating component during southwest monsoon season and fall transition months is not in agreement with the in-situ data, while the lateral advection is in agreement with the in-situ data. And the summary is that the SST during the warming phase depends equally on the cooling rate during the previous season, and also the Indian cooling during the northeast monsoon season is favored by lateral advection and the residual term, and the vertical entrainment contributed to warming during northeast monsoon season, and also it's contributed to cooling during spring transition months. And the Indian cooling during the southwest monsoon season of negative IODR is favored by the resultant heat flux with the support of large loss of latent heat flux and decrease in short wave. And also thin mixed layer depth favored larger loss of penetrating component below the mixed layer depth during the southwest monsoon season and fall transition months of 2016. And the warming during the fall transition months of 2019 is driven by one-dimensional heat flux terms. And I thank you once again for the patient listening. Thank you.